In this lesson, we talk about the antiderivatives, or indefinite integrals. First, we are going to talk about what is an antiderivative and its basic properties. We'll talk about the notational issue as well. The students who are already familiar with properties of antiderivatives and indefinite integral notations may just skip to the second part and third part of this lesson. For the others, here we go. Let's suppose that small f of x is the derivative function of capital F of x. Then we say that capital F of x is an antiderivative function of small f of x, and we use this notation here. We read like this: capital F of x is equals to integral f of x dx. This symbol over here is the integral symbol, and it comes always with dx, just like opening and closing parentheses. And the function that we start with comes in the middle, and we call this function the integrand. This variable of the integrand, x, must match with this x of dx, and also the variable of the antiderivative function. Antiderivatives are in general not unique. That's because derivative of any constant is 0. Here's an example. Antiderivative of 2x is x squared. Yes, you can take the derivative of x squared and you're going to get 2x. However, not just x squared, but x squared plus 1, x squared minus 45, x squared plus square root of 17, and so on and so forth, are all antiderivatives. They're infinitely many. In order to capture them all, we use plus c, arbitrary constant. We call this constant integral constant. Here are some jargons here that you have to remember. The function we start is called the integrand. The resulting function is called the antiderivative, or indefinite integral. And the plus c that comes out at the very end is called the integral constant. Alright, let's talk about some rules of antiderivative that will help us doing the calculation. First, let's go with some trivial rules. Antiderivative of 0 is arbitrary constant. Antiderivative of constant k is kx plus c. Antiderivative of sum is sum of the antiderivatives. And antiderivative of some coefficient times function is coefficient times the antiderivative. Why are they true? Well, we can simply take the derivative from the right hand side. Derivative of c is 0. Derivative of kx plus c is k. C will become 0, it disappears upon taking the derivative because it's constant. And upon using the power rule, we're going to get just k here. How about the other one? It follows from derivatives rules too. So derivative of sum is sum of the derivative, and this f prime, capital F prime, is nothing more than small f of x, and capital F g prime is small g of x, so we ended up with the integrand back again. This is the same. Start from the right hand side and then take the derivative. This capital F prime of x is the same as a times f of x, so we ended up with the inside. These trivial rules are easy and we can get used to these very quickly. Important rules begin from now on. I'm going to introduce 3 elementary functions: the power functions, and reciprocal function, and exponential function. The power function can be the antiderivative of power functions become like this. It actually comes from the derivative of the power function. Well, What is derivative of the power function x to the k power? Power is multiplied and subtract 1 from the power. Because the antiderivative is backwards procedure, we do precisely backward. What did he do? Multiply and then subtracted 1. We do precisely backward. Add 1 and then divide. Raise the power by 1 and divide by the power. Of course, that doesn't work when k is -1 because denominator is 0 here. In that case, what we have? Well, this antiderivative is, this integrand is actually 1 over x. What kind of function gives you 1 over x upon taking the derivative? It's of course a logarithmic function. So the answer is log function. However, log functions have to have positive number inside. Therefore, we take absolute values to make sure the inside is positive. To be more precise, we can actually do this kind of computation. Take the log derivative of the log function when x is positive. This is straightforward. Derivative is 1 over x, consequently x to the negative first power. What if what if x is negative? Then log of absolute value of x will be log of negative x. Upon taking the derivative, we are going to get, well, this computation. Inside goes to denominator. By chain rule, we have to multiply the derivative of inside. That's -1. We end up with 1 over x again, the reciprocal function, consequently integrand x to the negative first power. Final rule, derivative of exponential function stays the same. That's because, well, antiderivative exponential function is the natural exponential function. That's because derivative of exponential functions stay the same. Now these are standard rules, but I'd like to introduce you a little bit extended form. Instead of x to the k power, let's consider ax plus b to the k power. Instead of x to the negative first power, let's consider ax plus b to the negative first power. And instead of e to the x power, let's consider e to the ax plus b power. In that case, what happens? Very same. Power rule, logarithmic function, exponential function stay the same, but the recurring theme is we have 1 over a in denominator. The reason? If you take the derivative of the right hand side, by chain rule we have to multiply the derivative of inside a. In order to undo that chain rule multiplication, we start with 1 over a, so that multiplication by cancel. Multiplication by a just cancel each other. Here's an example. Start from the right hand side and let's take the derivative. What happens? Well, this plus 2 will disappear because every constant will become just 0, and the derivative of this part by chain rule will become k plus 1 will be just multiplied, and then we have to subtract 1 from the power. That's not all. By chain rule, you have to multiply the derivative of the inside. It's a linear function, so derivative is just a. That's going to be multiplied here. So what did he end up with? A times k plus 1 divided by a times k plus 1 just cancel each other, and we ended up with ax plus b to the k power, the integrand. We ended up with the function we started from the first place. The other formulae can be driven pretty much the same way. Those are left as an exercise. The recurring theme 1 over a comes from the chain rule, and that's gonna be these three will become very, very useful